Hi, folks. We're going to take a look at some examples of taking derivatives using our initial derivative properties. So here we've got a polynomial, and so let's go ahead and take its derivative. So y prime, or the derivative of y with respect to x, is equal to, well, here I've got a sum and difference of terms, so I know the derivative of these sums and differences are just the sums and differences of the individual terms, and I see that I've got these coefficients. So I'm going to have to use all of my properties here. So first of all, the derivative of 3x cubed is the same as 3 times the derivative of x cubed. Okay, that's the constant multiple rule. Then I have minus the derivative of x squared, then plus, well, the derivative for x can be rewritten as 4 times the derivative of x, and then here minus the derivative with respect to x of 12. All right. So now I've got this constant in front, and now I can take the derivative of x cubed, and using my power rule, I know that that's equal to 3x squared. Then minus the derivative of x squared is 2x, plus 4 times the derivative of x is just equal to 1. And then minus, well, the derivative of any constant is just equal to 0. And now finally I can simplify this to get 9x squared minus 2x plus 4. All right. Now, just to give you a heads up, I don't actually expect to see this written out every time. You might want to do it the first couple of times you do these derivatives, but eventually you should be able to go directly from this function to its derivative, because you can do all the side operations in your head. Okay, that you think of this as, well, 3 times 3x squared, 9x squared. Okay, 4 times, we'll derive x is 1, just 4. All right, so I would start quite quickly trying to go directly from a polynomial to its derivative. All right, so if I take a look at the second question here, well, I have a power of x. It's just not quite written that way. So what I'm going to do is rewrite this function as x to the 4 over 3, so that I've written it as a power of x. And so now I can easily take the derivative using my power rule. Okay, so remember, the exponent becomes the coefficient, and the exponent goes down by 1. So 4 over 3 minus 1 is like 4 over 3 minus 3 over 3 is just 1/3. Okay, and for now, we're going to leave our answers in this form. I'm not going to require you at this point to rewrite them and say in root form. All right, let's look at this last one here. Now, I've got a quotient of two functions. It looks like it can take the derivative of the numerator. I can take the derivative of the denominator. But at this point here, we saw that the derivative of a quotient is not the quotient of the individual derivatives. So I'm going to have to find some other option here. Well, one thing I can do is I can simplify this expression. I can break up this fraction into x cubed over x squared, which is just x, minus x to the 1/2 divided by x squared. So 1/2 minus 2 is negative 1/2. So negative 3 over 2. All right. And now I've written in a form with which I can find the derivative directly. So again, here you're going to see that I'm not going to write out that I'm taking the derivative of this difference, or the difference of the derivatives. I'm just going to do it in my head. Okay, so the derivative of the first one, derivative of x, is just equal to 1 minus, now the derivative of this expression, again, I'm going to use brackets to make sure I don't make any silly mistakes. The original exponent now becomes my coefficient, and then my exponent goes down by 1. So negative 3 over 2 minus 2 over 2 is negative 5 over 2. All right. And this is just 1 plus 3/2 x to the 5 over 2. Okay, and like I said, for now, we're going to allow ourselves to leave it in this form. Okay, so at this point here, the only derivative rules that you have are the sum difference rule, the power rule, and the coefficient rule. So you're going to have to work within that framework. So this is why in part C, it was necessary to first do some simplification, even in part B, to rewrite this root as an exponent so that you could use one of those initial rules that we have. All right, that's it for this one.